Hello and welcome back. This time we're looking at paper 1 from November 2022. This is for Edexcel IGCSE 9-1 and it is paper 1, so it's 4CPO/01 is the course code. Okay, well, it's a 2-hour paper and it's 50% of the total marks between paper 1 and paper 2. Total marks for this particular paper is 80 marks and we're going to be focusing primarily on assessing your knowledge and understanding of the basic principles of computer science. You can pause that if you want to. That's just an overview of paper 1 and of course an overview of paper 2. So we begin, and this is what you'll get. Paper 1, IGCSE 9-1, the course code, and it is principles of computer science. Here, like every other paper, we're going to be writing in black ballpoint pen. For Edexcel, you're going to put your name and everything else on. Yeah, the marks are shown in brackets. The important part though, the one I wanted to bring up, you are not allowed to use a calculator. Remember to read every question and all the rest of it. Okay, but yes, although this is computer science, you are not allowed to use a calculator. Okay? So we'll get started. Remember, you should try and answer all the questions. Okay, so we'll look at the first question. Computer systems have both hardware and software components. The central processing unit, the CPU, uses the fetch, decode, and execute cycle. State what is meant by the term program instruction. An instruction is basically like an instruction if you're given an instruction by your teacher or by your parent or by whoever. It's something, and it's as simple as this, something that tells the CPU what to do. Okay, that's basically it. Or what to do, what action to perform. Okay? That's it. That's basically, for 1 mark, something that tells the CPU what to do. Yeah? Good. State what is meant by the term memory addresses, part B. Memory address is basically identifying a location in memory. Okay? Identifying a location in memory, a point of reference. Okay? I'm doing 2 parts, but basically identifying a location in memory. Okay, part B. Okay, well, let's have a look. Identify the components of the CPU that provide temporary data storage. Well, is it the address bus? Well, the address bus is not correct because a bus is carrying information. In this case, it's carrying the address of the memory location. And it's saying for B, the data bus is carrying the data, not stored data, but it's carrying data. And C, it's not correct because the control unit is sending signals from the CPU. Okay, so the correct answer must be D. The performance of the CPU is affected by the clock speed. Give 1 benefit of having a higher clock speed. It can carry out more instructions in a set time, e.g. per second. Okay, that's one idea. The programs execute faster because the processors run faster. So that would get you, well, it says 1 benefit. So carry out more instructions per second is probably the obvious one, and the programs execute faster because the processors run faster. That would get you the mark. So either one of those. Okay, when it says give 1, always only give 1. If you give 2, 1 counts as the other and you get no marks. Give 1 drawback of having a higher clock speed. We're sort of talking about overclocking here, so it could overheat, okay? Could run too hot. Therefore, we could add to this, therefore, more cooling would be required. Could overheat, therefore, more cooling would be required. It also needs more power, so I think that will do. So could overheat, therefore, more cooling would be required, it needs more power. Okay? Any of those, I've given you 3 there, could overheat, more cooling is required, needs more power. For part D, identify which one of these describes a sequential computational model. Well, sequential means one after the other, a sequence. 1, 2, 3, 4. Okay? 1, 2, 3, 4. A sequence of events. Okay, so let's have a look at this. Program instructions are read one after the other. Okay, that's good, yeah. From external storage. No, that's external storage. Nothing to do with computational models, so we can dismiss that one. Program instructions are executed by multi-agents. Well, multiple agents, no, that describes instructions that are coming from all over the place. Program instructions are executed in parallel. That means more than one at a time, different cores. So that's no good. Basically, it's D. Why is it D? Because program instructions are executed one after the other. That is a sequence of events, okay? Yeah, not necessarily from an external storage. So the correct answer would be D. A program can be written in high-level or low-level language. Give one reason for writing a program in low-level language. We're talking here about machine code. Machine code is used when writing code for a particular device, okay? Not for a general purpose computer. So that is what I'd write. I mean, there are others, or to control a specific device, okay? So it could be something in a factory, something maybe in a bottling plant, moving a bottle from one place to another. It just does a certain thing, and that would be used. You could write that in a low-level machine code language. Okay, state the purpose of an assembler. Now, an assembler is very similar to a translator, but instead of converting high-level language into low-level language, basically it translates or it converts. So it converts assembly language, and there you see the link, assembly language into machine code. Okay, so it can run on a specific device. Now, for 3 marks, complete the table by adding 1 tick in each row to match the description. So we're still talking about translators. Okay, so it translates a program each time it is executed. Well, this is similar to if you had an interpreter who was interpreting you speaking in one language and changing it to another. They would translate one part at a time, one sentence at a time, so to speak. So that would be an interpreter. Produces permanent object code. Well, this does it all in one go, so it converts the code into object code, which would be a compiler. Translates line by line. Again, it's the same thing as mentioned in the first one. This would be an interpreter. Translates the whole program before it is run. Again, similar to the second one, it is a compiler. And now then generates a list of errors once the completed program has been translated. Well, this is the same as before. It translates it all in one go, and then it spits out a list of errors at the end. Okay, it doesn't give you an error and stops. So that would be a compiler as well. So that would get you your full 3 marks. Okay, and for this one, each row can only have 1 correct answer. You can't say that they're both. 1 mark is awarded for 2 correct rows, 2 marks awarded for 4 correct rows, and 3 marks have been awarded for all 5 correct rows. 1, 2, 3, 4, 5. Okay, and that will get you 11 marks for part 1. Okay, question 2, part 2. Computers use binary to represent and store data. The denary number 78 is the ASCII code for the character N. This doesn't matter at all. It matters in the next bits. Convert the denary number 78 into an 8-bit binary number. Okay, so it's basically 2 nibbles. So what I'm going to do here is do a little 1, 2, 4, 8, 16, 32, 64, 1, 2, 8. Basically 8 numbers, 8 different numbers. Do we have any 128s? No. 64 will go into 78. So we go 78 minus 64 would equal 14. Would have 14 left. Okay, so that means 32 doesn't go into 14, 16 doesn't go into 14, but 8 does. Okay, so 14 minus 8 again equals 6. So that would mean we've got a 1 there. So 6 minus 4 equals 2. A 1 there minus 2 equals 0. So we've got none left, which means the last number would be 0. So the correct answer is 01001110. Okay, and because it says 8 bits, we need to include this first 0. Okay, identify the number of characters that can be represented using standard ASCII. Standard ASCII, if we're talking about 8-bit, and this is where the link is, yeah, is 128 characters. So the correct answer there is B for standard ASCII. Extended ASCII would give you 256. Okay? But we move on to the next one. Give one reason for using Unicode rather than ASCII to encode languages other than English. Unicode allows for many different characters of 16-bit. So if we talk about 128 and doubling every time, so 13-bit would give us 256, 512, 13, 14, 15 would give us 1028, and 16 would give us 2052. But it goes from 16 bits all the way up to 32-bit, which would give us many, many characters, somewhere in the region of 65,536 characters. So Unicode allows for many different characters because it uses a minimum of 16 bits up to 32-bit, equaling 65,000 characters. Okay, so that would give us the mark there. 128 characters is not enough. And then finally, B, convert the denary number minus 43 to 8-bit binary using sign and magnitude representation. Sign and magnitude. Sign and magnitude. Well, this is how I'd do it. I'd go 1, 2, 4, 8, 16, 32, 64, minus 1, 2, 8. Okay? So I'm going to start off, because it's a minus number, I'm going to put a 1 in this box here. Now I'm going to try and get to minus 43. Okay? So to get to minus 43, I've got to start adding things to this minus 128 to get to minus 43. So if I add 64 plus 64 to minus 128, I would have minus 64. I'm not going to add 32 to it, because that would give me minus 32 and I want minus 43. But what I could do is add minus 16 to it. So plus 16 would give me 48, minus 48. So I'm not going to add 8 to it, but I'm going to add 4 to it to give me minus 44. I'm not going to add 2 to it, but if I add 1 to it, I will end up with minus 43. But this method is using 2's complement, but we don't want it in 2's complement. We need it in sign and magnitude representation. In order to do that, but sign and magnitude representation is even easier. So minus 1 is the MSB. This is the MSB, which basically means the sign of the number. Okay? The MSB. So I'm going to put that there and label it MSB so we know. And then we basically work out what 43 is. So 43 would be no lot of 64. It would be one lot of 32. 32 add 16 would give us 48, so that's no good. But 32 add 8 would give us 40. We can't have that. And then, of course, we would have one for 42 and another one for 43 equals minus 43. So we're basically taking the positive, but this time adding a digit. It can be either at the front or the back, which is the MSB, to dictate that this is the minus. Okay? So you've got an example there in 2's complement, but this one would be the sign and magnitude. Okay? So that's how I would do it. It's very easy, actually, very easy. The other way, I think, would work if I flipped it around. Complete the table by adding these two 8-bit binary numbers together. Well, this is nice and straightforward. Remember, we can only have ones or zeros. So 0 plus 0 is obviously 0. 1 plus 0 is 1. 1 plus 1 is 2, but we can't have 2, so we've got to go 0 and carry the 1. Okay, 0 plus 1 would give us 1, nothing to carry. 1 plus 1 again would be 0, with 1 to carry. 1 plus 0 plus 1 would give us 2, which is 0 and 1 to carry. 1 there, and then 0 and 0 would give us 0. So the correct answer is 0, 1, 0, 0, 1, 0, 1, 0. An image is made up of pixels. An image has 5 colours. Complete the table by adding a unique binary pattern for each colour. Each pattern must use the same minimum colour depth. Okay, 5 colours. If we had 2 colours, it would be either 0. 2 colours would be either, so 2 would equal 0 or 1. Okay, 3 colours would have to be 0, 0, 0, 1, 1, 0, 1, 1. Okay, 3 and the same for 4 colours there. But 5, we would need to add 3. So we could go 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, and then we could possibly do 1, 1, 1s at the end. Okay, it would basically be 3 bits. So I'm going to put in here 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 1. Okay, and there's any number of answers you could have for that. These are all unique. Another image is 3,579 pixels high and 6,128 pixels wide. The image is stored with a 32-bit color depth. The metadata for the image is 732 bytes, basically the location of it and when it was taken, the date. Construct an expression to show how the file size in megabytes is calculated. You do not need to do the calculation. Okay, well, first of all, I'd times everything together. Well, I would times 3579 times 6128, and then I would times that by the color depth. Okay, that would be my first thing I would do. The next thing I would need to do is to get it from bits into bytes. I would divide it all by 8. So, step 2, bits to bytes, divide by 8. Once I've converted this to bytes, I can then add on these 732 bytes. So add the 732 bytes. And then because I'm going to megabytes, I'm going to divide by 1000, would give us kilobytes. Yeah, from bytes to kilobytes. But because I'm going to megabytes, I'm going to divide by 1000 times 1000. Convert bytes to megabytes. Okay, so it would look something like, if I was to do this as a formula, let's do this in a different color, I would have 3579 times 6128 times 32 plus 732 divided by 1000 times 1000. Okay, and again that would give us a total for question 2 of 15 marks. Okay, question 3. Alyssa is a music producer. Figure 1, the table here, shows the denary values of 5 samples of an analog sound using a sample interval of 0.2 seconds. Okay, what we've got to do is take that data, complete this graph using the sample information from figure 1 to show the digital sound wave. So we're basically moving from an analog wave, which is something like this, to something that's more like this. So we've got sample numbers. This y-axis goes up to 12 and the x-axis 1.0. Okay, so let's break this down a little bit further. So 5 samples, and these samples are taken every 0.2 seconds. So sample 1, which basically is here, was taken as a denary value of 1. Okay, so I'm going to push that along there. That's the first value. So it took a sample at 0.2 and the value was 1. Now, at the second sample, the value was 10. So what I've got to do is, because it's digital, I'm going to go up to 10 on here and across. Now realistically, in the exam you should be using a ruler. At 3 we've got to 12, so again I'm going to go up like that to 12. At 4 we're down to 5, so down here. Okay, and at 5 we're down to 3. Okay, so that would be my digital sound. Okay, and it stops there. So first sample, like this, is 1, second sample 10, 12, 5 and 3. So that's how I would complete the graph. So that would be the first part, and that should get me the full 3 marks. Okay, but please remember to use a ruler. Now it says, give a suitable label for the x-axis. That's this one down here. Okay, well the x-axis is these values here. Well, these are the sample. For this label, I would call it the sample interval. Okay, every 0.2 seconds. I mean, you could still get a mark if you just put seconds, according to the mark scheme, and you could get a mark if you put time. But I think the best answer, based on the question, would be sample interval. If we then move down, give a suitable label for the y-axis. Well, the y-axis, if you think about these curves like so, this is the amplitude. Okay, this is the amplitude. So again, I'm going to put in here amplitude. That would be the answer. Or volume, or you could argue volume. Yeah. I think the mark scheme does talk about meters, centimeters, and nanometers, but I don't quite know how that fits in. Alyssa uploads music files to her cloud storage. She compresses the files before she uploads them using lossless algorithms. Well, you wouldn't really use lossless algorithms on sound files, but okay. Give one disadvantage of using a lossless rather than a lossy algorithm for this purpose. Well, lossless, they're not going to compress by that much. It's basically less compression, meaning a larger file size. Less compression meaning a larger file size. So obviously that's going to take up more space on a disk, and it's going to take longer to transfer that data or save that data to the cloud. Explain one benefit, but because it says explain, yeah, we're going to go into a bit more detail here too. Okay, 2 marks. Explain one benefit to Alyssa of storing music files on the cloud. Well, because they're on the cloud, because they're on the internet, she can access these files from anywhere in the world. I'll put with internet connection. What else? Less space needed on our drive. Okay. No need to perform backups. Files will not get deleted by accident. Okay. What else have we got? Give one possible security issue associated with storing music files in the cloud. Well, what do we know about security and the internet? It could be targeted by hackers. Those people who wanted to sort of steal this music. They could be targeted by hackers. I'm just trying to think of another one. Has less control over these files. Alessia has less control over these files. Basically, if she hasn't got access to the internet, she cannot get hold of her files. If she's somewhere where there's no Wi-Fi connection, she can't get hold of her files. Okay. One of Alyssa's music files, I'm calling her Alessia or Alyssa, one of Alyssa's music files is stored at this website here. Complete the table by adding a description of each URL component. We've got to basically break down these URLs. So, hopefully you've remembered these names. The HTTPS is the protocol. Okay. Also, S equals secure. Okay, I'll put that in brackets. www.cloudisfab.com. What is that? Well, that's the domain name. RE12. That's obviously a folder where this ru2.mp3 file lives. So RE12 is the folder. Okay. But you could also name this folder or path. Yeah, either one of those. Don't put both. Folder / path. And then ru2.mp3 is obviously the file name. Yeah, music, because it's an mp3. Okay, so you've got the protocol, the domain name, the folder or path, and finally the file name, the music file, ru2.mp3. And that should get you 13 marks for that question. I'm going to leave it there for part 1 because we're already over 20 minutes, and then we will move on to part 2 in the next video. Okay, thank you very much indeed for watching. Please continue to ask questions, leave your comments, hit notifications, and please subscribe. And finally, if you wish to buy me a coffee, I'd be truly grateful. Please visit buymeacoffee.com/learning zone. Thank you very much indeed. See you next time. Bye for now.